Hello. Today we're going to talk about the fundamentals of probability. So, first, let's talk about some of the basic terminologies of probabilities. And we're going to first start off with outcomes. Outcomes are simply the most basic possible result of observations or experiments. So, for example, if you flip a coin two times, you can say that one possible outcome is getting a heads on the first coin flip and then tails on the second coin flip. The example I have written here is just saying that when you flip a coin once, you end up having two different outcomes, one being heads, the other one being tails. The next term we're going to talk about is an event. An event, which oftentimes will basically give it a capital letter like A, B, C, or so on. This basically consists of one or more outcomes that share something of interest. Let's say, for example, if we were to flip two coins and we are trying to figure out what the probability is of getting one heads, right? Well, either the first coin or the second coin could be a heads. So that means that that event has two different outcomes, one being heads and the second one being tails, or the first one's tails and the second one's heads. So then we have what's called the sample space. And the sample space simply lists out all possible outcomes. So for the first row in that table, we have the procedure where we flip a coin once, and the event is just getting a heads, so there's only one outcome in that case. However, we have two outcomes as we mentioned before. We have heads, and then we have tails. What if we flip two coins? Well, there's two ways that can happen for getting one heads and one tails. We have heads tails and tails heads. But if we list out the entire sample space, we end up having those two that we just mentioned. So heads tails, tails heads. We can also have heads heads. And then lastly, we have tails tails. So it turns out that there are, in fact, four different possible outcomes for flipping two coins. If we flip three coins, and let's say we're trying to find the event where we get one heads and two tails. Turns out there's, I believe, three different ways this can happen. First one's heads and the last two are tails. We can have the case where the second one's heads, or we could have it where the last coin is heads. So now, what if we were to list out the sample space? I would start off with actually writing it kind of maybe a little organized, where maybe we have all three coins being heads. Then we'll list out all the cases where we have two heads and one tails. So there's three different ways we can have two heads and one tails. Of course, we can also have the three that we mentioned earlier in our event. So we have heads, tails, tails, uh, tails, heads, tails, and then tails, tails, heads. And the last one I haven't mentioned yet is where all three are tails. So it turns out that in this particular case, there are 8 possible outcomes. Now, this might seem weird where we went from 2 to 4 to 8, or maybe you do happen to see a pattern here. Now, this is jumping ahead a little bit, but the idea is that for the first coin, we had 2 choices, second coin had 2 choices, and the third coin had 2 choices. And it turns out that if you multiply them together, you'll get all 8 possible outcomes. So now we're going to continue talking about some of the basics of probabilities, and we're going to look at the notation that we're going to use. Now, we're using this notation P parentheses A, and we have to be a little bit careful on this notation here. P parentheses A does not mean we're taking P times A, like other times where we use parentheses and have some number in front, that usually means we're multiplying. Think of this being similar to f of x. So this is a function notation. I know we haven't really talked about it much in this class, but think of it in terms of this where we're saying the function name is f and x is the independent variable. So anytime you see p parentheses a, think of it as just being the probability of whatever's inside parentheses to occur. So for example, if we let A be the event of getting exactly 2 tails when flipping 2 coins, then we know that there's only one possible outcome out of those 4 uh, total outcomes. Now, we have to be a little bit careful in this case because there's actually three different ways of finding probabilities, and they can actually give us slightly different results depending on the scenario. So, what we actually were looking at here, with the probability of getting exactly two tails when flipping two coins, that's actually the theoretical approach or the theoretical method. Then we have the relative frequency method, and then the last one is the subjective method. The subjective method, in my opinion, is basically just an educated guess, where you have so many factors that can cause the event to occur or to not occur that it's just basically too difficult to try and get an exact probability. The example I have here is just calculating probability of one of the elevators in Jonas breaking down today. Now, you can kind of guess based off of previous experience or knowledge, and maybe guess that's fairly low. So, what we're going to focus mostly in this class is the other two methods, which are the relative frequency and the theoretical method. The relative frequency is pretty straightforward. You just count how many times something occurs, and you divide it by the total number of times that you observed something as the procedure is running. So you can kind of think of this as flipping a coin 5 times. So let's say when you flip a coin 5 times, you get heads, heads, tails, heads, heads. Maybe you end up just getting 4 heads and 1 tails. And let's say we're trying to find the probability of getting heads in one coin flip. Well, based off of our 5 coin flips, we would say the probability of getting heads is 4 out of 5, or 80%. Now, of course, this isn't quite what we expect to have happen. In fact, we would kind of guess that this probability would be closer to 50%. That 50% comes from the theoretical method. So the theoretical method is basically looking at the number of possible ways an event can occur and divided by the total number of possible outcomes. So this isn't where you actually go and repeat a procedure over and over again. This is just theoretically looking at what can happen and divide by all the possible things that can happen. So if we look at probability of getting the heads in the coin flip, we would expect that it'd be 50-50 because you have one out of the two possible events that can occur. Suppose you're rolling two six-sided dice. What's the probability that the sum of the two dice is 4? If we look at the theoretical approach, we need to first figure out how many ways can we roll the dice in such a way where the sum of the two dice is 4, and divide that by all possible outcomes of rolling the two dice. So what I'm going to do is I'm going to write them in pairs. So I'm going to write 1, 1 to represent the first die as a 1 and the second die as a 1. And then I'm just going to continue on here. So what I've written down so far is just listing out all the different outcomes where the first die is a 1 and the second die is some other number. Now I'm going to do this where I change the first die to 2 and then just repeat. There probably was a fast way of figuring out how to find the number of outcomes that we had in total. And if we think about it, if I picked 1 for this first die, notice that there were 6 different ways that can occur. And there were in fact 6 different numbers I could have picked for the first die. So it turns out that there are 6 rows and 6 columns. So in total there are 36 possible outcomes. Now, how many of these will add up to a sum of 4? It turns out that it's only these 3 here, where if we take 1 plus 3, or 2 plus 2, or 3 plus 1, we'll end up with the sum being 4. So that means that this is a probability of 3 out of 36, or 1 out of 12. And 1 divided by 12 is 0.083 repeating, or 8.3%. There are 52 cards in a standard deck of playing cards, and we're excluding any jokers. So let's say we select one card at random. What's the probability of selecting a card that is either a jack, queen, king, or an ace? So this may help to actually look at an actual deck of 52 playing cards. And if we count these, we'll notice that there are four cards per suit that are either jack, queen, king, or ace. And if there are four suits, that means that it would be 4 times 4, which gives us 16 cards out of the 52. And this, of course, simplifies down to 4 out of 13. And 4 divided by 13 is 0.30769, and so on, which is about 30.8%. So now let's look at the complement of an event. And I do apologize for the spelling error. So the complement of an event A, you can almost think of it as the opposite of that event, meaning it's the probability in which that event does not occur. So let event A be drawing a diamond card from a standard 52 card deck. What is the probability of drawing a diamond card? Well, there are 13 diamond cards out of the 52. So the probability of A is equal to 13 out of 52, which, of course, there are four suits, so you can also argue that it's 1 out of the 4 suits, which is 25%. So now what's the probability of not drawing a diamond card? Well, you could just count all the other cards, and that would give you 39 out of the 52 cards. Or what we could do instead is we could find the probability of not A as 1 minus 1/4, which we know is just 4/4 minus 1/4, getting that common denominator before I subtract, and we're left with 3/4. Now you can also reason this as being the fact that there are 3 other suits, so it must be one of those other suits out of the 4. And this can also be written as 75%. So next we have the multiplication rule. And this is basically the principle or rule that I've been using a little bit earlier, where I was counting the number of outcomes for the dice, or the number of outcomes when flipping a coin. And this basically works where you have some number of possible outcomes for one process, and then some other number for the number of outcomes for another process. And basically, you just end up multiplying them together. So you can kind of think of these playing cards as having 4 different suits, and there are 13 unique card values. So if we're trying to figure out how many unique cards there are, we would take 4 times 13 to get 52. Now, of course, if we have more than 2 different types of processes, we can basically just keep multiplying the numbers together. So if we were to flip 4 coins, we can find that there are 2 choices for the first coin, 2 for the second, 2 for the third, and 2 for the fourth. Multiply those together, and we get 16 possible outcomes. Now, I probably didn't leave this in the handout, but it probably doesn't hurt to go over this problem. So let's suppose you decide to order a 2-topping pizza from Domino's. And there are 3 different types of styles for the type of crust. There are 5 different sauces that you can pick from. And you want to have 1 meat topping and 1 non-meat topping. And for the meat toppings, there are 10 choices, and then there are 16 non-meat toppings to choose from. So we're trying to figure out how many different 2-topping pizzas are possible with these restrictions. So taking it one step at a time, I'm just going to highlight what we have to customize. So we have 3 styles for the crust. We have 5 choices for the sauce. We have 10 meat toppings, and then 16 non-meat toppings. Since we have to choose one of each of these different options, that means we're just going to multiply all of these together. So we're going to take 3 crusts times the 5 sauces times the 10 meat toppings times the 16 non-meat toppings. Multiplying these together, and we end up with 2,400 pizzas. Now, this doesn't, of course, include all 2-topping pizzas. You can have pizzas where they have 2 meat toppings, or maybe they choose 2 non-meat toppings. And that gets a little bit trickier to count, so we'll avoid that for now. So, when selecting one card at random from a 52 card deck of playing cards, what is the probability of selecting an even numbered card where we exclude face cards, meaning that we do not treat face cards as being even? Well, if we list out all the even cards, we have 2, 4, 6, 8, and then 10. And there are these numbers for each of the suits. So that means that we have 5 numbers and 4 suits. So there are in total 20 different ways we can have select an even card. So that means that our probability of getting an even card is equal to 20 out of the 52. This simplifies down to 5 out of the 13, or we get 38.5%. Thank you for watching, and I'll see you in the next video.